you're not on P, you can recursively determine that you're not on P. But knowing that you are on, that P is on the attractor, is something that is in my view likely to be an uncomputable or undecidable proposition in a finite decision process. So that's a slight aside, but we'll come back to that again. Now, so I wanted to say, I said that I'm trying to de-emphasize this word chaos and unpredictability and emphasize other aspects. And I'm emphasizing some of these other aspects because of the relevance, the possible relevance to the Bell inequality and such like. So one particular sort of key thing, I think, and something that certainly, Lorentz, nobody before Lorentz had guessed that this was likely to be true, was that, his interest was turbulent fluid mechanics. And it's known, if you look at a turbulent fluid, it's got potentially zillions of degrees of freedom. And the view was that to explain the complexity of turbulent flow, you needed zillions of coupled differential equations to describe those zillions of degrees of freedom. And what he was able to show was that completely non-periodic behaviour, so nothing repeating itself, looking apparently random, behaviour could be generated through motion on a very low-dimensional subspace. For example, n dimensions in a state space that could be 2 to the n, for example. So this, for me, this is getting away from unpredictability and saying one of the key aspects is that you can generate very complicated, apparently random behaviour on a sort of invariant set, which is very low, potentially very low dimension compared with the number of degrees of freedom that the system may have in reality. Now, a second aspect or a second property of this type of deterministic non-periodic flow, non-linear property, is that you can, and this is actually used in practice a lot in practical studies of chaotic systems, is that you can actually construct, or what's called reconstruct, the whole geometry and shape of the attractor in phase space by just monitoring or measuring one of the degrees of freedom of that system. So, for example, with the Lorentz system, that's just got 3 components. You could just take the z component and just look at, measure the value of the z with a certain, every sort of t seconds or something, measure z. So you produce a time series of just one of the degrees of freedom. From that time series, you can reconstruct the whole three-dimensional, or the attractor as it lives in 3-dimensional state space. So this, in a sense, is quite a dramatic thing if you think about it. I mean, if you were listening to, it's sort of a bit like saying, if you were listening to, Beethoven's Fifth Symphony, could you reconstruct the entire symphony by just taking one of the second violins out and just looking at the musical score? Well, you couldn't. I mean, all you'd have is the musical score of the second violin. So, this is, in some sense, runs contrary to perhaps one's intuition, that here it's like saying you can take just 1 degree of freedom out and sample it enough times, and you can know enough about the entire system from that just 1 degree of freedom. I just put here shades of Mark's principle. I mean, this kind of vaguely reminds me of, by looking at the inertia of just one little particle locally. In some sense, that's, if you believe in Mark's principle, it's telling you something about the mass of the whole universe.
Tim, are these theorems?
These are theorems. This is called the Tarkin's embedding theorem. This is a very famous theorem in nonlinear dynamical systems theory. Yes, indeed.
What's the deal with?
Oh, sorry, degree of freedom. This is a degree of freedom. So, in other words, one of the many dimensions, if you like, that make up state space.
Yeah.
So just,
So, for example, if you have a gas and you just follow one molecule of the gas for sufficient amount of time, you'll be able to...
Yes, it could be one of the. Yes, that's right. If it had this underlying
So would so
governed by this underlying type of
oh, I mean, it has
dynamics.
to be governed by a low dimension.
Yes, yes, that's
But
right.
it has to be non-linear. at some-
Absolutely,
somewhere.
absolutely. It has to be non-linear, yes, absolutely.
It's less counterintuitive than you think. If you have a bunch of jazz musicians and you know them very well, then you could actually sort of expect from
Yeah.
what one plays
You
what
knew-
the rest probably
yeah,
was
yeah,
doing.
yeah, maybe.
So
It's interesting. Another way of sort of looking at this, this, by the way, I hope this will come apparent in a sec, why I'm trying to get at this. I mean, in a sense related to this second point here, is that you could take one of these degrees of freedom, one of these directions in state space, even though energetically, it explained like a zillionth of a percent of the energy of the total system. So it'd be very unimportant. If you perturb it in an arbitrary way, you will almost certainly, with probability 1, in the sense with respect to the continuum measure, if you like, of your state space, you will take that system off the attractor. So the attractor lives actually, for these chaotic type systems, the attractor is actually a measure 0. It has 0 measure with respect to the continuum measure. So it has this kind of fractal structure in this low dimensional space. So if you sort of slightly move the state off, perturb the state in some arbitrary way, maybe a sort of what you think of as an infinitesimally small perturbation, you'll take it off the attractor with probability 1.
But then it will go back to the attractor if you let it evolve.
It'll go well if you allow the system to evolve under the differential equations. It will then go back towards the attractor. But what am I trying to say here? Oh yeah, what I want to, I'm going to come back to Bell in a second. But just to come back to your point, what I want to think of here is a system which, if you like, is the attractor set itself. So I want to think conceptually, for what I want to think about here, I want you to think of the attractor as an intrinsically defined set, independent of how it's embedded in this Euclidean state space. This reminds me, when one tries to talk to, people, lay people about, people often ask, how can the universe, you say the universe is somehow finite, but it's got no boundary. So you say, well, imagine you're an ant on the surface of a football, you see. That football has no boundary, but it's finite. And then you say, well, you have to just imagine the universe is a three-dimensional version of that football. But then people have difficulty, because then they say, yeah, but what about the direction away from the football? What's happened to that one? And so you have to say, no, don't think about that. Don't think about how that football's embedded in three-dimensional space. You've just got to think about the intrinsic geometry of that football. And that causes a lot of difficulty. People don't understand that. So, that's lay people. But this is what I want you to think about. I want you to think of a system which is just defined as flow on its invariant set. I don't want you to think about the fact that this is embedded in some Euclidean space. Now, I'm going to, in the next talk, there is a methodology for doing this, which is called symbolic dynamics, which is part of nonlinear dynamical systems. It's not a very common thing. But you realise, this is a kind of difficult thing to describe mathematically, if you like, the intrinsic geometry of this type of attractor, kind of independent of its embedding. But that's the thing I want you to talk about. So if you perturb the system off the attractor, then I've kind of gone out of my allowable. The system is no longer part of my system now. I'm out of the system. That's a key point. Because I want to come back to Bell now again. So just to recap, we started. I started with a quotation from Bell, and he's making the point that the whole conclusion that quantum